Hello, my name is Jancarlos Gomez, and today I'll be covering home cooking robots. What are home cooking robots? Basically, they are robots that are capable of helping users in the kitchen by creating dishes on their own or assisting the user in the creation of dishes. Cooking robots tend to have the following characteristics. They learn by teaching by doing. They consist of a multitude of sensors. They work in conjunction with sensor networks around the kitchen. They tend to have robotic arms and or legs with 6 to 7 degrees of freedom to replicate the human anatomy. They use machine learning, trajectory planning, simulation, and visualization, require software infrastructure in order to operate. We can observe a robot model being simulated and visualized on the right-hand side to open a drawer in the kitchen. There are mainly two types of cooking robots, cooking assistants and automated cooking chefs. Cooking assistants require significant user interaction. They tend to be humanoid robots. They have limited capability in the kitchen so far. They are mainly used to dictate recipe instructions, locate items around the kitchen, monitor user progress, or complete simple tasks as we can observe this HRP2 robot is doing, which is pouring a bottle of liquid into a cup. An automated cooking chef, on the other hand, requires minimal user interaction. The user really only has to obtain the ingredients and the cookware and provide it to the robot and select a recipe. And this can be broken up into two main groups, partial cooking chef and full cooking chef. On the bottom, we can observe a Mali robot that is making a steak dish all on its own. Cooking robots consist of a multitude of sensors. Acceleration sensors are placed on cookware in order to detect how fast a knife, for example, is moving. Ultrasonic sensors are placed on the robot. RFID readers are placed to read the position of food items and cookware items. Laser ranger finders to make sure that the robot does not crash into anything. A microphone so that the user can input commands vocally. Robots tend to have various cameras, for example, standard cameras, stereo cameras, RGBD cameras, which are used for color and depth perception, infrared cameras, CCD cameras. Magnetic position sensors are used on the robot joints to see how much the joint has moved. Force sensors are applied to robot tips, for example, on the hand, so we can see how much pressure is being applied to an item such as an egg to make sure that it doesn't crack the egg. Temperature sensors are also applied, display screens, speakers to give the user instructions. These robots tend to work with sensor networks around the kitchen. Cooking robots cannot reach everywhere in the kitchen, and these sensors that are placed strategically around the kitchen, for example, over the oven, over the sink, um, RFID tags that are placed on cookware and food items allow for the detection using an antenna on the robot, a laser rangefinder to detect areas that the robot cannot detect due to its position, and drawer sensor, magnetic sensors to alert the robot that a door, kitchen drawer may be open. In the future, we expect more products to come with RFID tags instead of barcodes from the store. So this is basically preparing for the future. On the right hand side, we can observe an RGBD camera looking overhead on top of a pot, which may give extra coverage to the cooking process, which the robot may not be able to see. These robot cooking assistants are able to monitor food and safety. They can detect when food items are ready. For example, we can observe the pancake on the bottom left. Once bubbles begin to form, the pancake is ready, and this is detected by the RGBD camera sensor. These robots are capable of giving instructions to the user via a speaker or by pointing. They can prevent hazards from occurring, such as when the robot is cutting something and the ultrasonic sensor detects that the human is nearby, it stops cutting to prevent harm to the user. These robots create consistency in dishes and prevent the users from ruining dishes. For example, if the robot detects that an item is about to be burnt, due to the change in color. It'll notify the user. On the right hand side, we can observe the model of how the robot interacts with the user. The robot dictates to the user the instructions, and the user conducts that instruction, and sensors in the kitchen and on the robot itself detect the events that are occurring, and then this gets compared to the steps outlined in the recipe instructions, and the cycle continues. Commercial versus research. The majority of cooking robots are in the research phase or are personal projects. The only commercial robot that is really available for purchase is the Moldy Robotics Kitchen. The main reason for this is that cooking robots are expensive and a niche market. This robot down here, the Moldy robot, costs about $340,000. They require a lot of space to install or store. This is basically a whole kitchen remodelation. And if you're going to have a robot assistant humanoid, you need somewhere to store it. They're, these robots are still in their infant stages. Algorithms are still being developed and optimized, and they need to be very versatile to adapt to everyone. A couple of challenges these cooking robots face are on the user end side. Users have a really hard time evaluating a cooking robot due to their limited function evaluation. People can't eat endlessly. We get full, and between meals, we have a fading memory, and we forgot what we previously ate. And when we try to compare and see if the robot's improving or not, it's very hard to evaluate the robot's progress when you're trying to tune the algorithm. There's also the concept of individual preferences. Not everyone likes the same kind of food or the same kind of salt or peppering, so that plays a role. Also, humans set future expectations based on past experiences, which is the grounding problem. If you had a bad dish previously and this robot prepares it, you might have a bad expectation because you didn't like the dish you had previously. On the robot side, or the developer's end side, deciding the correct grip position for each item is a challenge. Deciding the order in which to execute tasks is another challenge. Translating recipe instructions to motion codes can be a bit of a challenge. Avoid creating hazards for the users, as we mentioned previously. Being able to work offline is a big challenge because the robot has to be able to handle the processing power and also have the software for it. Optimizing the algorithm to meet the user standards for flavor, texture, and appearance. The size of their robots, some are too big and they really can't fit everywhere, and the ability to constantly learn and do new tasks. How are these recipe instructions evaluated? Well, this is the motion planning phase. Cooking robots basically take a recipe, they extract the keywords from it, and then they replace these words with a motion code equivalent. There are 8 different types of motion codes. For example, there is tool, food, seasoning, and basically these motion codes are sorted, and they're sorted into the appropriate order, which make logical sense. And that's how recipe instructions are executed. Hierarchical task networks. Cooking robots tend to work in a hierarchy approach and decide how to execute tasks based on the weight and options available. So if a user defines one path with greater weight than another, the robot is more likely inclined to take that path. For example, in the pour Q X into Y, the robot has a greater weight to go autonomous. So it goes to take X, and once it goes to take X, it goes into another hierarchy. And inside this hierarchy, there's some kind of constraint that disturbs the hierarchy. There's maybe a failure backtrack, which means that an item that the robot was looking for is not in the kitchen or is not visible to the robot, and the user needs to interact with the robot and help by giving the robot the item, as we can observe. There's also other things that can disturb the hierarchy, such as user-defined constraints or changes in the symbolic state. Changes in the symbolic state really affect the motion planning, because if the drawer had to close 18 inches, but instead we modified it to 20, we would have to modify the motion planning. On the left-hand side, we can observe that this consists of primitive tasks, which make the TN task description. This is made up of sensor action, user interface, special motion, motion planning, and position generation. Then the recipe database and the supervisor state all go into the task planner and form the hierarchy. How does a cooking robot decide on how to grasp items? Well, a research project conducted by 2 European universities highlights how an AR MAR robot decides to grasp items in the kitchen offline. Humans have 16 different grasping hand positions. This is a 4-step process for picking a grasp. First, the robot uses its cameras to detect the shape of the object. Once the shape of the object is detected, if it's in the database, it will go straight to the grasp that it needs to do and do it. If not, a set of candidate grasps are generated based on the shape. On the right hand side, we can observe that using image processing, the shape is generated on site offline, and the robot has a 3D model and can simulate a set of candidate grasps to generate, and then it chooses the best one, and this grasp is stored into a database. The previous method that used to be used is that the developer would have to make a 3D CAD model and then upload it to the robot, and the robot would have to compare with the database. But this way the robot can actually do it everything offline using the method described on the right hand side. Here we can observe 5 different ways of grabbing items: a hook grab, cylindrical grab, spherical grab, a pinch, a tripod. And we can observe how a humanoid hand, rotates to position itself to grab a bottle. There's also an algorithm that's been used to improve user expectation. A UR5 robot was used in the UK to improve user expectations with the Bayesian optimization algorithm. Basically, the batch Bayesian optimization is better than the sequential Bayesian optimization because it allows inputs to work in parallel. So it's better for the robot to work in batches instead of sequences. You can observe how the improvement of using batches far outweighs sequential in flavor, appearance, and texture. The UR5 robot can be observed on the right hand side. It is preparing an omelet. In conclusion, we explored several different features that make up a cooking robot: sensors and sensor networks, recipe translation, trajectory and motion planning, simulation and visualization with regards to grasping items, machine learning. Cooking robots still have a long way to go in regards to affordability. It is quite costly. Commercialization, there's really only one model available to the public to buy right now. User friendliness, current ones we've seen are in the research phase and they require a lot of the developer to interact with the robot. It's not good for the average consumer. The size, most of these are too big, and adding a plethora of features to make them more utility. Representative video and project references. First video highlights Samsung's commercial bot chef, mainly featuring trajectory planning, sensor networks, and limited human interaction. You can observe the bot chef cutting a piece of tofu. Second video demonstrates cooking assistant robot in the research phase. The video demonstrates teaching by doing, trajectory planning, and sensor networks. The robot is learning how to grab a cup, and the following references were used in this project. Thank you for learning about cooking robots with me.